So I'm Anupama Kowli. I'm an assistant professor in the electrical engineering department. We've been doing this course on Internet of Things, and some of the work that I've been doing can be construed as a case study of Internet of Things applications for energy utilization. In particular, if you see, the room you're sitting in is a live test bed for me currently. A lot of the sensors that you see, these are sensors that I've been utilizing for my work. So we'll be talking about precisely the background behind this work, what are the things we are doing on the way, potentially introduce you to some analytics as well. So here's a rough outline for the next hour and a half or so. What I'm going to do is first quickly go over the background and motivation for this, and I will discuss some of the preliminary investigations that we had conducted on the IIT Bombay campus that eventually led to this project. Then I'll specifically talk of the project that we have currently ongoing under the MHRD Imprint scheme, and because this is a IoT course, I will also give you an overview of some of the analytics, some flavor of the analytics that would be needed to actualize some of these results, and some concluding remarks. Okay, I expect this session to be fairly interactive, so if you have any questions, please feel free to stop in between and ask. I don't have that many slides, neither is there too much material. A lot of the things are going to be interactive, so I would expect questions to come on the way. Alright, so what I have here is a plot on the air conditioning loads, or rather air conditioners. How many air conditioners do we expect to see projected into the future? We are currently here where India is in violet. So we don't have that many air conditioners, but this is expected to become every sixth air conditioner in the world is expected to come about in India by 2050, and very valid reasons for this, right? We have a hot tropical climate for most part of India. Wherever there's a lot of human civilization, it also coincides with hot tropical climates. We have a significantly better economy than some other nations, which means we also have that buying power to go ahead and procure air conditioners for ourselves. So we are going to have a lot of air conditioning systems connecting onto our electricity grid, drawing power from the grid, okay? And this is very tightly coupled in some sense. This cooling requirements that come, they are very tightly coupled with sustainability development goals. Anybody knows what these are? Have you heard of sustainability development goals, SDGs?
Solar renewable energy amount can be 2030 has been decided to.
So those are our broad targets. By 2022 we need some solar energy. Those are the targets set by the government, but sustainability development goals is something that the UN has come up with. It's a framework under the United Nations. So for a very long time human beings have done development in some sense at the cost of nature. Sustainability development goals means you bring about development not at the cost of nature. It has to be sustainable development. It has to be something that does not have an adverse impact on the nature resources around you, natural resources around you. So I think the two biggest goals that I remember, the first one is habitat for all, clean habitat for all. The other one is energy access to all. I specifically emphasize on energy because energy sometimes is very often synonymous with electricity. That's not true. Energy is energy. Electricity is a form of energy. But in the SDGs, one of the, it's either goal number 1 or goal number 2, I don't remember, it means you need to have mechanisms with which everyone in the world has access to clean, sustainable energy, okay? And a big part of energy consumption and big part of livable habitat, so both SDG 1 and 2 are very much coupled with whether you have cooling, right? Whether they have conditions in their homes, conditions in their offices that make them comfortable, whether they are able to be productive. So cooling is very tightly coupled with both these goals. So although it is not actively a sustainability development goal, figuring out sustainable ways of cooling our buildings, our homes, it's a very big goal that we should have recognized. Yes?
I was just wondering,
countries like United States and China,
Yeah.
obviously the cost is more in terms of heating rather than cooling.
It's I'm not aware of China because I've not lived there much. I've
But the
lived in the
US,
US,
yeah.
and the US summers can be very, very hot. In fact, the biggest blackouts in US have happened during summers.
During summers.
Yeah. So
would you not want to take the total cost rather than, I mean, just cooling and not cooling and heating put together? Because the principles in a way would be similar.
So for me, I came about it from a cooling perspective because in India we don't have a need for, I am no longer in the US, so I don't need to care about sustainable heating. But you're right, that is another angle to this. So a lot of people actually work on what they call as HVAC systems, which is heating, ventilation and air conditioning. In India, we don't have the concept of HVAC, we just have air conditioning. And if I figure out that bit for India, I think my problem is solved, someone else's problem may not be solved.
And the reason, I'm just wondering, is it because India is much higher in terms of the load? I think it's kilowatt hour is what you're showing on the.
No, this is just, I'm sorry, it's not, it's just units. How many million units of air conditioners sold? I'm going to come to your question in just second or third slide, but in terms of kilowatt contribution, I have that slide as well. Any other question? All right. So this is just a closer look at India. I believe this could be a building that could come from somewhere down in South Bombay. Any of the government offices in South Bombay, if you look at it, they look like this, you know, a lot of split air conditioners hanging off the windows, or it could be a building in Delhi, I don't know. I'm not sure this actually is it was a news article published in a newspaper and I just picked it up from there. The source is linked right there. The article actually talks about why India is the best place to really rethink how air conditioners should be designed, how they should be worked about, how should we actually utilize air conditioners because of the climatic conditions here, because of how much use of ACs we are going to see in the foreseeable future. This is roughly the AC energy demand in India currently. So it's about 135 terawatt hours. So tera is 10 raised to 12. Huh? And this is going to, the fractions may not change significantly across the next, let me see, where is this? I think this is supposed to be in 2038, yeah. So 20 years from now, but it's going to quadruple. So although the fractions may not change much, the AC load as such is going to quadruple in the next 20 years, and that's going to be a huge demand. So there has already been a lot of efforts put in by our, so this is Ministry of Environment, Forest and Climate Change. They have already initiated something called as the India Cooling Action Plan. The report was released in 2019 March. You can take a look at the report. These are figures that come directly from the report. So because the demand is supposed to quadruple so much in the next 2 decades, there is also work they're talking about where they say efficiency interventions and any other intelligent ways of using ACs, either at a design stage itself or when you actually use them, can in fact reduce this demand by 30%. So that means instead of quadrupling, it's just going to become 2.5 times potentially, which is huge for us, right? Also, if you look at it, why do I care? So my training is actually, I'm a power engineer by training. I've been trained as a power systems engineer. I work in the big wire market, right? So why do I care about the air conditioners and how to control air conditioners? Here is the motivation for my work. What we have here is the current contribution of the AC load to the peak load we see on the Indian grid. It's roughly at about 10%. Okay, in the 2050 scenario, it is projected that this contribution to AC loads is going to go up to 40%. So 40% of the megawatts that the Indian grid would experience during peak hours is going to be directly attributed to air conditioners, and that's a huge load, right? And if we were to just, instead of actively doing anything, even if we were to just make the air conditioners more efficient, not energy guzzlers, just better use of air, better design of air conditioners, we can bring down that demand, that contribution to 20% or less. right? So already by just rethinking how the air conditioning systems should work, you can in fact really bring down how much demand you are imposing in terms of megawatts on the grid. And what we show is, if you can actively engage the air conditioners, not only do you have potentially reduce the peak load on the grid, but you have also, you can exploit that source as some sort of flexibility for the grid. For instance, right now you are sitting in this room. If I was to turn off a couple of these air conditioners, there are 7 ACs in this room. Yeah, 7 ACs in this room. If I was to turn off 2 of these air conditioners for just 10 minutes, right? Would you be uncomfortable? Just 10 minutes, right? Not really, right? Okay, if I turn them off for 30 minutes, potentially yes. But if it was a half full room, then if I turn them off for 30 minutes, do you think they're going to be uncomfortable? Right? So there are various parameters on which I can actually actively take decisions. Why does it matter? Why does it matter that I turn off these air conditioners for 10 minutes or 30 minutes or whatever? When would I potentially need this? One at a time, please.
At the time of peak, ma'am.
At the time of peak, you may want to do this. Someone here? Peak hours, okay.
Manage the frequency, balance the
You could need it as a way to balance the frequency in the grid. You could also need it as a backup for your solar and wind, right? What is our, so someone mentioned this target right now, you were talking about the, by 2022, we want a lot of solar and wind power to materialize on the grid, correct? One of the biggest challenges with solar and wind is we cannot make the wind blow when we want it to, we cannot make the sun shine when we want it to, we just have to produce whatever they give us. A big part of that means that there is also some uncertainty. We cannot perfectly know exactly how much production we are going to see coming from solar or wind, okay? So if we had assumed that we are going to get some 10 megawatts of power from some part of Maharashtra, let's say. What actually happens in real time is there's a big cloud cover around that same time, and instead of 10 megawatts, what you get is 5 megawatts. Where would you produce that additional 5 megawatts? It could come from other states, but that means that we are going to have some interstate unscheduled flows, correct? It could transiently, of course, come from the inertia of the generators itself, so which means we are going to see a change in frequency. In either case, these are not the mechanisms that are necessarily having any long-term sustainability to them, right? It is not a long-term solution that you keep relying on frequency dips or you keep relying on trades. On the other hand, the utility in Bombay, right? We get power from Tata. Tata says, oh, there is 5 megawatt deficit right now. Can IIT Bombay drop its load by 10 kilowatt, let's say. IIT Bombay imposes a 10 megawatt peak load on the Tata power grid currently, right? So they are not even asking us to drop a fraction, it's like less than it's a very minuscule thing. But they take 10 kilowatts from here or maybe 100 kilowatts from here, and then they take 100 kilowatts from some other big campus. They go to other academic campuses, they go to other government buildings which would have already have solar and also have cooling loads on them. And by just consolidating a lot of these reductions, they can easily produce 5 megawatts of deficit that was created by solar backing down, correct? All you have to do is just back down some air conditioning load, 10 minutes, and roll it across as well, correct? If you want to do this, what would be the determining factors? So let's say at the grid level, someone somewhere just tells IIT Bombay drop 10 kilowatts. How should IIT Bombay respond to this request?
Look at your major load areas.
Okay, but that could also mean that there could be a bunch of students who are engaged in classes at that time, and then they are going to go and talk to some news agency and say IIT Bombay made us very uncomfortable. We had to sit in hot, humid rooms and learn in inhabitable conditions. I mean, we get a lot of flack for many things. Imagine the hula that would create if we just cut down the air conditioning loads, right? So you go there, but is it enough to stop at that? You go to the major load areas and say, okay, this is where I want to drop load? Is there other? Okay, great. Wherever it's not required, how do you make that decision?
Based on
We are getting to the crux of.
the IoT sensors.
So you basically this very question that she said, wherever it is not required, you drop the load. How do you decide wherever it is not required? IIT Bombay is 500 acres. I cannot have a human being going around, going into each classroom and saying, is this the right place to drop the air conditioning load? Is this the right room? I don't have that. By that time, that 5 megawatt drop created by solar would have passed, and there could have potentially been a 5 megawatt excess you have to deal with now, and the chance has passed, right? So we need quick ways of deciding this, and IoT is a very good way to materialize these sort of things, right? You can potentially get visibility into what is happening in classrooms very quickly, get that visibility very quickly, process that information, and then find out if this is the right place to drop the load. So in a room this size, for example, if I had sensors which were mapping out the occupant density in the room, my sensors would tell me this is a full room right now, perhaps not the best candidate for load reduction, because all ACs are going to be loaded to their max and are required to be loaded to their max, correct? Best way to just get that decision across. So you just need maybe some occupancy sensors. You also may need to know actually what the temperature in the room is going to be. So maybe some thermal sensing, right? Humidity perhaps, because a big part of Bombay is humidity. In fact, a lot of the comfort that we feel is not just temperature related, it's very much related to humidity we perceive as well. So you do both sensing. So the sensors you're currently seeing in front of you, these are measuring temperature and humidity. There is a setup downstairs which we are going to showcase how we are also sensing occupant density. So distribution of occupants across space, okay, not just whether there is one occupant or not, but also distribution across space. And we are going to look at these case studies, and then what I'm trying to do here is weave a story around what this information could be used for and what could you actually potentially do with this. Makes sense? Any questions? All right, okay. So as I said, the whole motivation behind this project was, can we do any better? Can we control our air conditioners better? So anyone knows what this is? Alexa and Google Home. So these are already in the market, right? What can you make Alexa do other than play songs and ask what the weather is and news reports? Sorry? You can switch on, switch off lights with it if you had a smart switch. Alexa doesn't, it needs certain other components to work with it. So if you had a smart switch which has Wi-Fi capability or some other form of communication capability, you can potentially use Alexa to switch on, switch off lights. What else? So currently this is the level at which Alexa is. What we want to do is pump it up, right? Now take something like Alexa. We are not going to call it Alexa, we will call it something else. But have you heard of home energy management systems? These are Alexa++. Thermostat is a small part of it. So there is something called as a smart thermostat. In fact, very much used in US and other places. So this is where they can intelligently set your temperature set points. Okay. But I'm not talking of just thermostats, I'm talking of more complex scheduling of the entire home. So in a future scenario where you are going to have electric vehicles coming in, where you are potentially going to have your own rooftop generation, solar generation available, also maybe a battery, and you have devices which are grid friendly in some sense, okay, which can in fact maybe not necessarily grid friendly, but at least amenable to control commands from some central unit. And this central unit could be your home energy management center, could be some aggregator that is not exactly at the home level but at a slightly more aggregate level, could be the utility company, whatever, but it has the ability to talk to your device. This could be your refrigerator, this could be your air conditioner, this could be your car, electric car, right? So with this ability, So there are sensors and actuators needed for this. With that, if you couple that with artificial intelligence, machine learning, analytics which are going to use this data, okay, and then intelligently decide how to run this, that is when we can really fully realize the potential of IoT, the potential of AI to bring about some tangible improvements which contribute towards smart cities, towards smart buildings, towards smart homes, right? Does that make sense? So what could you do with this potentially? What is the vision I have? Where do I want to go with this? I am driving an electric car, okay? I want a parking lot where I can charge my electric car. I'm going to go to office. Maybe this parking lot, if I have a dedicated spot in my office itself, great, everything's solved for me, right? I just go there, I park right there, I plug it in. Now there is a building manager that is going to interact with the grid, correct? And maybe you have signed up for some maximum demand you impose on the grid, but the number of cars in the parking lot far exceeds this maximum demand, right? Or the number of cars in the parking lot and the number of air conditioners in my office that are running exceed this maximum demand. What is the potential of IoT to do something meaningful for me? I may not even have to go to that. That is where, that brings in, that's also a great idea. You could actually just take batteries themselves in the cars can be used to provide some support. But that means that there's a bi-directional flow. You're actually using them as a service back to the grid. I may not even have to go to that. I have a simple dream. What I want to do is I want to charge batteries of the cars in a staggered manner. They don't have to come all together, right? They don't have to impose total demand on the grid at the same time. I should be able to figure out, oh, there is, the CEO's car is parked right there and he is a busy man. So I want to charge that with priority, right? And then the intern, low-level intern, maybe his car, I may not charge with the same priority, okay? Even though there is, of course, going to be a deadline, a hard deadline for each of these cars. By 6 o'clock in the evening, all these cars should be charged, but the CEO's car has to be charged, at least, has to be charged 90% or something. You get it to the 90% state of charge level, whereas the intern's car, I'm going to take a hit and say, ठीक है, 80% तक भी चलेगा. He gets lower priority. Or if he's willing to pay for it, I'm going to be a savvy businesswoman and say, do you want guarantee on your charge being up to 90% level just like the CEO? Pay me a premium and I'll make sure that your car also gets the priority. So either you get priority because of your status or you get priority by being, able to pay for that priority. Whatever be the case, whatever way you define this priority, right? You should be able to decide how many cars get charged at what point in time, and you can do it concurrently. If you are the building manager, you also have visibility on the loads in the buildings, the air conditioning loads in specific, right, which typically contribute 50 to 60% of the energy needs of a building, electricity needs of a building, correct? So here, basically now I have to say my conference room is not going to be occupied till 4 o'clock in the afternoon. That's when there is a team meeting there. So I don't need to run that AC at all because I have sensors in the room that are telling me if the room is in use or not. I have information that comes from the schedule as well. Typically, there are more complex organizational schedules and so on. I can leverage the schedule information, I can leverage the actual sensed information, and then make sure that whatever demand I'm imposing on the grid is below what I have actually signed up for. Because if I violate that, then the utility can actually slap a penalty on me, correct? Now if the grid further asks me, that same 5 megawatt deficit from solar scenario comes about, I also know what my candidates are going to be to drop load. All the non-priority vehicles which were currently being charged because I had slack, those are the ones I'm first going to drop. No intern vehicle will be charged at that point, right? So these sort of actively, you can make active decisions by having sensors in place, by having actuators in place, and further, not to forget, you need to close the loop from sensing to actuation, so you need to have the right sort of analytics in place. Does that make sense? Everyone with me? All right. So sensors have been used in energy management for a very long time. There's absolutely no two ways about it. In fact, these basic, you might have seen these PIR sensors, right, being used in bathrooms or in any hallways or any common spaces for a very long time. The PIR sensor, it's a basic sensor, it's just an infrared sensor. If you sense that there is a occupant in the room or there are 10 occupants in the room, it just creates a 0-1 signal, right? It doesn't have the ability to distinguish that whether there is one person in the room, whether there are 10 people in the room, but it can sense occupants, right? It's a 0-1 sensor, and just by use of that you should be able to turn on or turn off your lights, correct? So this has been in use for a very long time. The other thing that people have also realized through social experiments as well as other more detailed technical, socio-technical experiments is if people are given information about their own energy use, they are more likely to be energy conservative. People tend to react to that information and take decisions in a manner that makes them more responsive to energy efficiency needs. Okay. Now this particular bit of results that a lot of people have derived, there's a bit of ambiguity as far as I am concerned in these results, because the control group may not be rightly chosen. If you choose very well educated people and you give them information, yes, you will see exactly these results. But if you choose people who really don't know how to even interpret that information, then you are not going to get anywhere. Unko just lagega ki there is something fancy sitting there, it looks very good, don't know any head or tail of it, and they cannot take any decisions. So I personally believe that a lot of these decisions need to, it's not enough to just collect information and display information, you also need to have analytics in place and actuators in place so that a lot of these decisions can be automated. Get the human out of the loop, really make it a true IoT system where information is sensed, it's analyzed, decisions are taken, and there's no human in the loop. The human intervention should only come at the design stage where you give in your preferences, right? That's what I would ideally want to work on, and that's what I'm working on currently. So we started this project with something called as the CampuSense project. This was funded by Cisco. And what Cisco wanted to do was actually just deploy all kinds of sensors across campus. So we had sensors deployed in our water systems, water distribution systems. We had sensors for air quality. We also had some sensors for environment monitoring inside classrooms. So what I was working on was only that part of the project. We had a classroom which was around slightly bigger classroom than this. It was a proper classroom. It was 250 seaters classroom. It was instrumented with 9 sensors. All the blue dots that blue rectangles you see here are basic temperature, humidity, luminosity sensors deployed inside the classroom. The 2 red dots you see here are again temperature, humidity and luminosity sensors outside the classroom, because we also wanted to look at the ambient conditions. This particular room had a sort of a centralized AC system. We call it the variable refrigerant flow system. What this means is there is cooling of air done outside, okay, or rather cooling of refrigerant done outside. The cooled refrigerant is circulated to what we call as these indoor units right here, and that is what is used to cool the air in these indoor units, and then the cooled air is circulated within the classrooms. This is how the cooling actually works, okay. Split is different. Split is you actually cool the air and the cooled air comes inside. This is refrigerant is cooled. So this is a variant of the variable air volume. You may have heard of this more. The centralized AC systems you will see with ducts, big ducts. That is where cooled air is being circulated. Instead of circulating cooled air, here we have a cooled refrigerant, and then the cooled refrigerant is used in these indoor units to cool the air and circulate the air. So slightly different system, but both central, in the sense that cooling is done in a central place, and then locally you have control happening to ensure that cooled air would be circulated within wherever the cooling is materialized, correct? Any questions? Yeah. So this was the classroom. This was the orientation of the classroom. This is where there were two entrances. These were proper solid walls. This is the glass surface. This was the outside exposure. This is where we had our windows and those sort of things. Okay. So the broad research goal, because Cisco just had the main goal for Cisco was that you use sensors and see what information you can learn. So we defined our own goals for our vertical. Our goals were to collect useful information, and we have useful in quotes because when we started out we didn't really know what would be useful at all, right? And then we wanted to use that information in some sense to optimize energy consumption for the classroom and also to avoid wastage as much as possible. So we've started off with something very simple. We wanted to, this is our actual system, whatever be that system, the entire thermodynamic system that's actually cooling, receiving some cooled air from the air conditioners, is also considering the use of air conditioners and the energy consumption that comes out of it. So this is the complete system, the building thermodynamic model itself as well as the air conditioners running in it. That what we are concerned about with how this system is consuming energy, okay? But we have wanted to have a model for this. And how do we want to build this model? We want to build model by sensing the environmental parameters, because the only sensors we had at that point were temperature, humidity and luminosity sensors. So sense the environment, create a model for this system and then use that model to devise control for the system. That was the broad goal we started off with, okay? This was the basic setup. We had those 9 sensor nodes which were equipped with THI sensing. Every 5 minutes we were sampling data from the sensor nodes. This was being communicated to a server via a gateway, and then this was being stored in the server and could be accessed either via a PC or a cell phone. Okay, these are the actual energy consumption parameter measurements. So because we wanted to build the model eventually for energy consumption, we also needed a way to calibrate the model. So we had meters installed for air conditioners, we had meters installed for fans and lights. So the air conditioning meter was a 3-phase meter because this was this big central system which was 3-phase load. The single phase meters we had for plug loads and fans and lights, okay? And these were also wireless meters. This data was also being communicated to the server every 5 minutes. This was what our interface was looking like. So we had temperature measurements coming in. This is measuring temperature, this axis, and then this black line here is actually showing you the current drawn by the indoor units. Okay, so there were 2 components to AC energy consumption here. One was of course the indoor units and how much they were consuming, and then there was an outdoor unit also which would also consume power. The outdoor unit was the one that was actually cooling the refrigerant. Okay, so this is just showing the indoor unit consumption. Now just to give you instances of how this data was used for analysis by us, this is the power consumed by the outdoor unit, this green line. This is the power that the indoor unit was consuming, and you can see that it's consuming some power during the night period when clearly the light is off, because this is a luminosity reading for us. Okay, sorry, this is the light current, but we also had luminosity readings for this. There was very low illumination, so there was no productive activity happening inside the classroom at all. The classroom was not in use. That was an inference we gave because the lights were off, but there was still AC on, and this AC was on most likely because the operator forgot to switch it off. So all the air conditioning systems in our classrooms, unless it's a setup like this, they are controlled through a central building management system, which means there's an active operator which is actually turning off and turning on units. We don't have simple remotes where we go. So this particular classroom is located in our lecture hall complex. That's a building that has an actual building manager who would turn off and turn on loads in the building by looking at an interface. This was just improper use of the interfacing. Okay. Now what we saw was across a month, roughly a month, or actually roughly 2 months, 1.5 months, about 340 kilowatt hours of energy was wasted in this room. Okay, that if I consider the residential tariff, it's not actually true, we don't pay residential tariff, but if I consider the residential tariff, that roughly means in that just single classroom, across a period of a month and a half, I had wasted 3,000 rupees worth of electricity, correct? This was roughly, we had also done calculations on how much energy is typically consumed by the room if it is running a class. So this was equivalent to running roughly 35 lectures, 1 hour lectures in that room, okay, across a period of a month and a half. So roughly energy equivalent to about 5 lectures per week was being wasted. 5 hours of lectures per week was being wasted. That is what I'm talking about. Now this classroom is a huge classroom, okay, so we typically use these sort of classrooms only for maybe 20 hours of teaching in a week. So if I'm wasting 5 hours of it, you can see how much energy is, that gives you some percentage of savings, right? So roughly 20% loss, just pure wastage of energy, correct? And this is because there's not enough visibility about what's happening. The operator is probably not trained, neither is there any immediate alert being raised to him that this classroom should not actually be using any air conditioner, and he's inactive, he's passive to it. The interface that they work on is very, very hard for them to interpret. So again, you can have all the information available to people. If they are not trained enough to actually use that information, they are not going to make any sense of it, right? This is a classic case. This person is a technician who's trained to become a building manager, but expose him to a slightly more complex management system than what he's otherwise used to, and he's going to take suboptimal decisions. You are going to have energy wastage, correct? So what our solutions want to work on is you try to get the human out of the loop as much as possible so that these sort of mistakes don't come about, right? Or you create solutions for them that are so intuitive that there should be an alert that comes in their face, and it should be very hard for them to ignore. You are wasting energy, you are like, there are these phone rings, cell phone rings, which make you very uncomfortable and you have no choice but to answer that phone call, something like that, right? That is the kind of solution we would want to work on. The other thing I wanted to talk to you about is, so the broad goal was very nice. Sense information, sense, analyze, react, or actuate some control, correct? But what we saw was these were off-the-shelf sensors we have purchased, okay? It's not like we built these sensors. These are sensors we have built, but at that point we had just gone ahead and purchased sensors off the shelf. And even these off-the-shelf, supposedly fairly standard market availability products, right? They could give faulty sensor information at a fair bit of frequency. So if I want to close the loop using the sensor data, which means I want to take the sensor data and actively use it for decision making, I'm not sure whether I can do that, because look at what this sensor is telling me. The temperature in the classroom is hitting 150 degrees Celsius. Boiler hai kya? It's a classroom. It cannot go to 150 degrees Celsius. Even this is ridiculous. It's saying it's 80 degrees Celsius. Can you imagine the headlines in Times of India if this is what we were exposing our students to? This is obviously faulty. So this was a malfunctioning sensor, because you can see that there's another sensor which is actually giving you something meaningful, 25. It's only this one sensor which has decided to go berserk. And we saw this at an alarming rate, in fact. Every few days we would see sensors malbehaving. So I couldn't directly use the data that came from the sensors for control, okay, or for any sort of model development, because this data was filled with a lot of outliers like we see here, or it was filled with just sudden spikes, or it was just stuck at sometimes. You have by this point, I believe, learnt about sensor interfaces and so on, right? So you can sort of just by some stretch of imagination realize that these sort of things could happen because battery drops down, your data acquisition system is not quite configured right. So you are going to get these errors. Measurement errors are going to be there. There are also going to be errors that come from the complete circuitry of that sensor node itself. So this is not very hard to conceive that would of this happening, which means that if you are going to use that information to actively make decisions, you should have ways to ensure that what you are working with is actually a clean data set. Okay. Thankfully for us, what came to the rescue was this classroom that we had actually instrumented with sensors. The space across which the sensors were distributed was not very large, so there was a fair bit of correlation between the sensors. They were quite correlated. Okay, just to give you an idea, this was the setup, right? This classroom was roughly the size of this, maybe about 30% more in terms of area. And I had already 7 sensors in this, right? So this, currently we have about 33 sensors in this, and even these sensors show a lot of correlation, correct? Just for some exercise now in, you talking and me taking a break, which sensors do you think may not be correlated with the other sensors? If you were to look at this particular setup, you can just, these are the names of the sensors, you can just call them out. Which sensors do you think are likely to be correlated, or which sensors are likely to not be correlated, and why? Outside sensors are obviously not going to be correlated with the inside sensors. Great. He took the low hanging fruit. Anything else? In the blue sensors.
VR and BL, you expect them to give you correlated value. You may not get a correlated value with MR.
Why do you think that's happening?
The physical proximity to each other, because they are more or less measuring the temperature within the.
And they are in the corners as well. So the BL and BR sensors are actually very close to the an external source of noise, which is your heat exchange happening through windows. Okay. So they would be very similarly affected, whereas this MR sensor, which is located right here, is not really that exposed to noise because it is further away from the doors as well. So that was not likely to be correlated with BL and BR, right? What else? Any other? BM and ML may be correlated as well. So let's take a look. This is where we have our correlation matrix. So these are the sensors. You can see all the readings that we have, and so this is the correlation matrix in some sense. They are of course all self-correlated, obviously this is their variance in fact, but you can see, let's see, where is BR and BM, and so you will have BR and BL is what we were looking at, right? So you can see this is BR and BL correlation, it's roughly 0.95, okay, and this is again it's going to be the same, I don't know why I made that mistake, it's correlation, it's the same, so it's 0.95 you can see, right? Whereas if you look at say BL and let's look at BL and MR, 0.83, okay. I'm sorry if you're not able to read this, this is the best I could do with the graph, but I'm reading it out to you. BL and MR is 0.83, much less correlated than BL and BR, right? And if you again look at, so BL in fact is only correlated strongly with BR, with any other sensor it is very poorly correlated. In fact, if you look at BL and the outdoor sensors, it's 0.4, the correlation. And you do expect some correlation because as the temperature outside rises, the internal thermodynamic system will also cause to heat up, but it's a cooled system, it's a controlled system, so it will not heat up to the same extent as the outdoor system. So you will see some correlation, but not completely correlated. Does that make sense?
It also has to do with the stuff like curtains and perhaps
so it's not a one-to-one heat exchanger. So even without air conditioning, you would still not see exact correlation because there is a heat exchange happening. It's not the same, right? So in fact, there are very standard sort of, you could build a first order model similar to an RC circuit to explain what happens to the temperature inside the room vis-a-vis what's happening to the temperature outside the room.
It also have to do with the fact whether you get direct sunlight there or not, or if it's a west wall as an example.
Correct. So that that first order model, the R and C could be tuned to ensure that all of these effects, shading effects and so on also taken. But remember, I mean, an RC circuit is like a low pass filter in some sense. So not everything that happens there would be translated here. In fact, this is a high inertia system in some sense, right? So you would have slower changes happening on this side compared to what's happening on that side, which is why the correlation will not be very high.
Did you keep the sensors at the same height, or were they hanging?
No, no. So in this room, they were at the
classroom. It would be difficult to do.
Yes, precisely. So I mean, it's difficult here as well, although mostly we have audience like you here, but even here people will fiddle around. So in fact, when I first started the experiment here and we had a DFM meeting, everyone was asking me like, what have you done? Is this recording device? I was like, it's just a sensor, it's just recording information. It is a recording device, but it's not recording voice. But we were having our department faculty meeting, which, as some of you may know, tend to get volatile at times. So they were all worried exactly what is being recorded. But we were not keeping it at this height, we were keeping it at the ceiling height. And our eventual goal is to keep it at ceiling height. These sensors we are only keeping at this height because we are currently in the process of creating a thermal map for the room. So we'll still have sensors at this height, but we need to know if this sensor is good enough to map the temperature here, because the comfort is perceived at this height and the sensor is at that height, and I'm going to talk of sensor placement as well in a little while. So this would be more clear in say 10 slides from now. Any other questions? Yeah. So this was the correlation I was discussing. Now how we were able to use this was because they were correlated. If in a group of correlated sensors, if there was only one sensor that was malbehaving, we could use that to flag that sensor and say, oh, this is actually not reporting the right data because it was not following patterns that were perceived from other sensors. So for instance, we were able to define a rule-based fault detection algorithm in this form. One was, we knew what would be the typical, if you look at the history of data, we know what is the typical temperature to expect in the room. It would typically not fall below 18 degrees Celsius, typically not rise beyond 35 to 38 degrees Celsius. So we had some min-max bounds on the temperature. We also knew, for example, what would be the rate of change. The data was sampled every 5 minutes. Right? And it's, as I said, it's a high inertia system. So you would expect it to have slower changes in some sense to the temperature, correct? So again, there is a rate of change in between successive measurements that's going to have an upper bound on it. It cannot go beyond that rate of change. The other thing was spatial relation with other sensors, which is exactly what he had discussed, sensors at the back versus sensors at the front, and also this correlation. So what I could do is sensors that were correlated or exhibited strong correlation together, I could fit basic regression models. So I could, for instance, take the BL readings and use it to predict BR readings. Likewise, I could take, for instance, FR and FL are correlated, as is ML and FR. So I could, for instance, predict the reading at FL using reading at FR and ML, right? And these sort of models could be built to check whether there is consistency in readings. If there is inconsistency, then I can also have mechanisms in place to flag which sensor is potentially the one that's deviating. The only problem with this algorithm is that if multiple sensors in a group would malbehave. So for instance, BL and BR were the only correlated sensors. And if both of them are giving readings within a range, but they are not exactly the same, then I don't know which one is malbehaving. Is it the BR that's giving the wrong reading, or is it the BL that's giving the wrong reading? And that's because I only have 2 sensors there. Or for instance, 2 sensors out of a group of 3 or 4 malbehave. Then again, it becomes very difficult to point out which sensor is malbehaving. So what we decided to do was, in fact, leverage the fact that it's a high inertia system and try to build a statistical model for what the temperature should have actually been like. Build a model for the temperature itself. What do you expect the BL sensor to be recording in the next instance based on what is the history we saw, correct? So we just built basically a sort of AI model for the temperature, and these were the features we used to build it. So we looked at a moving average, we looked at a standard deviation, looked at the signal to noise ratio, looked at all these features, and based on this and what we perceived the sensor should be reading, we were able to flag whether the readings from a sensor are actually faulty or not. Because if it does not observe accordance with its own history, then we potentially know whether the sensor is malbehaving. The only problem in this case, and we have not tested it out extensively, is I'm not sure whether this can catch bias errors. Sensors are prone to bias. Over time they tend to drift. Now depending on how the bias creeps in, because I'm not a sensors person, so this is something I need to understand carefully. I'm not sure whether a bias phenomena will be captured here, because there are certain features that would potentially, bias will be equally affecting all those features and may not actually be flagged. So that is something we need to figure out. We have not yet figured out whether we can catch bias errors with this or not. But with this we are certainly able to catch random noise, where outliers are easy to detect. In fact, just with basic min-max bounds you can detect outliers. So outliers is a no-brainer for me. But even sudden spikes, they may not be exactly like an outlier, but you'll see a sudden jump. So it's able to predict that also, rather detect that. It's able to detect stuck at X. So if a sensor is constantly giving the same reading, 38.8 or whatever, 28.8, we are able to detect those errors as well. As I said, I'm not sure whether we can detect bias errors at this point. I'm also not sure if temperature and humidity sensors are that prone to bias errors. So that is something we need to investigate and figure it out. But it could be potentially a limitation of this approach.
The sensors are of similar type, and if they are of similar age, if they have, then the bias that would creep into them would more or less be same. So as an overall room, you would end up getting a similar amount of bias across the room, not only at a particular sensor. The probability of being that
I'm not well equipped to comment on that, because I don't come from a sensors background at all. But bias, so it's very hard to determine the age of these sort of sensors in some sense, right? And some of this actually we may not have procured at the same time as well. So it's very hard for us to determine whether it's really the same age of the sensor. And it's not very clear to me that if they are of the same age, bias error would be something that creeps in approximately at the same time for everyone. That's not very clear either, because from a grid perspective, I've seen, for example, CTs and PTs, current transformers and potential transformers, bias errors really creep in arbitrarily depending on the loading and something. So even if I had two CTs commissioned roughly at the same time, but their loadings and all and the use on them is different, it just depends on how the bias errors would creep
tend
in.
to be more passive.
The
sensor devices
exactly.
tend to be more passive rather than the example that you're giving.
Correct.
And most of the sensors, the aging is defined as a specification.
Correct.
It's defined.
Yeah.
So
correct.
perhaps that could be a way of.
Yeah, that could be a way. So we have to look at that phenomena. Yeah. Any other questions or comments? All right. So this is just a way for to show how we were able to detect faults. This had roughly 99% accuracy, the second algorithm that I showed you. The other thing we tried to do, again a very ambitious project, was just take the readings of the temperature sensor alone and try and figure out if I can detect instances of AC switching on or AC switching off. So look at the temperature gradients. Okay, whenever the AC turns on, whenever the AC turns off, and not surprisingly, it was easier for us to predict whenever the AC used to turn on. Those instances we were able to predict with a fair bit of accuracy, but whenever the AC used to turn off, the temperature gradients were not very well defined in that case. That would really depend on how many occupants are in the room, how they are seated and so on and so forth, and that made it very difficult for us to detect whether the AC was turning off or not. And the reason we wanted to do this was simply because we wanted to have as minimal sensor interventions as possible. We did not want to have a smart meter installed at each air conditioner or at each plug load, which is going to tell us if the AC is consuming power or not. We wanted to see if this information is embedded within the temperature sensors itself. And unfortunately, this was not a very successful exercise. Although what we did see was the gradients of a temperature gradient in a full room versus a temperature gradient in a sparsely filled room, they were different in some sense, you know, and it's expected because it affects directly the thermal load on that. If you were to think of the RC thermodynamic model, right, the thermal load on there, the heat exchange is very clearly coupled with the number of occupants in the room. And as these number of occupants changes, the dt by the rate of change of temperature is directly getting influenced by that, and because of that we could see it, but we were not able to completely map it. I have to mention at this point, we didn't really have any good ways of mapping, figuring out occupancy either. We were relying on biometric data, which anyone who's been to IIT Bombay before can tell you is a very messed up system. Students sometimes don't like giving biometric attendance at all, or half the times they come to me and say ki record nahi ho raha hai ma'am, kya karu, and then they'll say a manual record to me that I did attend your lecture. So that biometric was not a very useful exercise at all. We did not have cameras installed, so there was no, and anyone who's actually worked with cameras and image processing in camera may also tell you it's very difficult to detect human presence using cameras. Okay, you get at best 90% accuracy, so that's also fuzzy logic only in some sense. So we didn't have cameras at that point either, so we really had no way to figure out number of occupants in the room. So it was a rough guess that mostly a full classroom based on biometric attendance, and we were able to see temperature gradients that were perhaps less steep as compared to temperature gradients in a sparser classroom and so on when the AC used to turn on. So there was some information, and which is why that useful in quotes was there. You know, there is some information embedded in these sensors, but it takes a lot of fieldwork and a lot of data collection to actually extract that information and make useful analysis from it. So after we were able to get some traction with ACs turning off or on, then we were able to also do some very basic rudimentary progress towards modeling of energy. But because we were so off in detection of AC turning on itself, or rather on was okay, but when it turned off, the accuracy of the energy prediction model was not very great. We were only able to do 60% accuracy. But we were able to generate alerts with this. So we were able to generate alerts for sensors that were not working. We were able to generate alerts for instances of energy wastage. So these sort of things we were able to do. That eventually led us to our own in-house sensing and actuation development, as well as development of analytics. So this was when the Imprint MHRD imprint scheme came about. So we put in a proposal for again sensing useful information, using that to optimize energy consumption, but we kept the goal of the project very simple. We really wanted to only control 3 parameters: fans, lights, ACs, that's all. Only 3 loads to be controlled: fans, lights and air conditioners. And the deliverables we promised them were, we are going to look at low cost sensing solutions, we are going to provide analytics, we'll have a web based interface for processing and doing analysis, and we'll have actuators to implement control, and eventually test beds like this, which would be used for live testing, field testing of our solutions and so on. Okay, so this was in some sense our IoT based energy management approach. So you're going to have sensors collecting data from the field. All of that data would be sent to a cloud, processed for fault detection, fault correction and so on. Once you have a clean data set, use that to model energy and then device control, and that control would be realized through actuators. We now had actuators for controlling air conditioners, we had actuators for controlling lights, we had actuators for control on, off and dimming of light and fans both. So fan speed control as well. Yeah. And you're going to see that below. We also had, in addition to the basic THI sensing that we were already doing, that was an off-the-shelf product, we developed our own THI sensors. In addition to that, the other thing we did was we also have a mechanism to just take PIR sensors and then also estimate the occupant density in the room. So big disadvantage of PIR sensors, which I mentioned earlier, is you are only able to get 0-1 decisions, right? Whether there is 1 or more occupants or not. So it's a 0-1 sensor. But we've been able to reconfigure the way PIR sensors can be used to not only say whether there's 1 occupant or not, but say how many occupants in some rough sense and where they are located. The reason I say rough sense here is because I will not be able to give you a precise count. See, that part is easy. I could just have 2 PIR sensors at the door and just direction of sensing can tell you whether the occupant has come in and occupant has gone out. For me, that was not what I was interested in. What I wanted to know was whether that part of the room is densely packed and this part is sparsely packed or not. So we were happy with fuzzy occupancy sensing. So we had levels. You go from 0 to 5, let's say. 0 being no occupant, 5 being a densely packed room. And in each zone, I would want to grade it as 0 to 5. That's all we were interested in doing. And we'll showcase a use case of that downstairs for you after this lecture is over. Okay. Now these are our sensor nodes. We have equipped them with, as I said, so this one doesn't have a PIR sensor on it. This one just has temperature. It has a BME sensor which is doing this temperature and humidity sensing. There is an LDR there for luminosity sensing, and additionally now we also have PIR sensors on there which would be used for occupancy sensing. Okay. The key advantages of this sensor node development that we have done here, and my staff downstairs would give you a bit more overview on how the development went about, is that we are able to use these single 4.5 volts 3200 milliampere batteries. We are able to make them last for 8 to 9 months. So these are extremely low maintenance sensors, thankfully not as many faults. So something we have not actually, that was not something we purposely went about doing, but somehow the data acquisition system here has worked in our favor and we are not generating as many errors with these sensors. That being said, we are still testing it with standard meters to make sure there are no errors, but I think these are fairly good sensors. The sensors we had earlier had a Wi-Fi based communication. These we have decided to go the RF route. So they are equipped with NRF modules which we use to communicate to the gateway. The gateway then wirelessly communicates to, or through LAN communicates to the server. Okay. So communication from sensor node to the gateway receiver is over RF. From gateway to the server is either through LAN or through wireless, whatever is more robust. Okay. What we also have on the sensors now is provision for local storage. So if at all there are issues with the Wi-Fi or the LAN connection, which means you cannot push data onto the server, there is onboard storage available where this data will be backed up, and whenever the Wi-Fi connectivity comes on, you are able to push it down to the server in a more intelligent manner in some sense. We are trying to, if the project gets extended, these are the two other things we want to do on the sensors, again to make them very easy to use. We want to do over the air programming. So every time we want to reconfigure the sensors, we don't want to get them down and rewrite on the rewrite the codes on it. So we just want to see if we can do over the air programming. And the other thing we want to do is USB powered charging. So the sensor doesn't have to, for the battery to be changed, these are rechargeable batteries, but if we could do it right there, just a USB plug that connects and is able to charge right there, that would be something that would be quite good for us to realize. We have not yet made progress on it, but we are working on it. The actuators that we have are, as I said, you can do on-off control, and you can also do either speed control or light intensity control with it. It's just basic regulation. The one thing I'm very proud of here is if you give me any AC remote, I'm able to create a remote for you of the same kind with Wi-Fi capabilities. So we are able to do that now. We have a unit which we call as the IR receiver cum recorder, which we then use to create these remotes with Wi-Fi capabilities for any other area. We are looking at a commercial deployment of this through Murata Business Engineering India Limited. So this was one of the products that requested us because they want any AC remote to be controlled. So this is what we are doing. And the only drawback here for us is there are some older air conditioning systems which don't even have an IR based remote. So we have not yet figured out how to embed those with Wi-Fi capabilities. We are working on that as well. The other thing we are also able to provide is a manual override. So for instance, you have a party in your house or you have a party here, right? And you don't want IIT to just control the air conditioners here because you have party and you really don't want to be uncomfortable. So there should be a manual override capability possible. So each of these solutions comes with a manual override. Someone is, if you want, you could provide a manual override to them. Okay, so this is the same room you're sitting in, so I don't need to talk about this. But this is the sensor placement graph I was talking about. So these are temperature readings from 4 different sensors, and I mean the reason I put horizontal here is because these sensors are placed on the same XY plane, but horizontally at different spatial distances from the air conditioner. So which one do you think is furthest from the air conditioner? Which one do you think is closest to the air conditioner? In other words, which is the increasing direction for distance from the AC? Correct? So that's increasing distance away from the AC. And this one is the vertical placement. So from on the Z axis, if I was to place sensors on the Z axis, which one do you think is closer to the ground? Sorry? Blue is closer to the ground or red? Red is closer to the ground? Okay, how many say red? Raise of hands. Red is closer to the ground. How many say blue? And the others are nota. This is increasing height, so increasing distance from the ground. Sorry, what were you saying?
Saying there were 2 arguments in my mind. One was where you have people, it will be more warm, but the other thing is that as it gets more warm, the air rises, so perhaps
yeah, so that's exactly the phenomena that's captured here. Also, typically the air, we've seen this, temperatures at this height typically tend to experience lesser variations than temperature on the ground, in fact. Okay, so that's exactly what's being captured here. Now this brings in an interesting angle, right? Now typically, just routing that point back to what you had asked me, this is what my sensor would be recording. Okay, but the ground reality, now this is exactly at the ground. So let's ignore this sensor, but as a human, maybe I am experiencing temperature at this height. This would be somewhere here, or you know, one sensor just stopped working at this point or was taken off, I'm not quite sure. But this is the sensor I'm actually interested in, because this is the one that's defining my comfort. And so look at the trajectory that sensor goes through versus look at the trajectory being recorded at the sensor that's deployed in field. So in the field, I'm going to be deploying this sensor. I cannot have a sensor here. But this is showing me this blue line, and this is showing me what I'm going to be feeling, which is the yellow line. And they're not the same. Okay? And they're not an exact scaling of each other. Although it may look like they're a scaling of each other, they are not. This is a sanitized environment where I could potentially even get a scaling. But if you know he sits here, the blue is going to record something else, and his presence in and around my sensor is going to introduce some additional noise, which means I'm not exactly going to be sensing there what he's actually feeling or what the environment he's placed in. So this brings in some very interesting challenges in terms of how do I use this blue sensor to really map into what I want to know. I want to be able to control air conditioners so that this yellow is well behaved, right? But I am not recording yellow, I am recording blue. How do I actually solve that problem? So this brings... There is correlation, but the noise part is very hard. So we have been trying ways to actually, one of my students is going to come at 4 o'clock and give you demonstrations of what other experiments we have been doing. There is a fair bit of accuracy with which you can predict that yellow, but it is not 100%. You cannot predict it 100% of the times, but maybe 90-95% of the times you are able to predict what goes on in the on the yellow as well. And we'll talk about that. The other thing is, I obviously also want to have minimal sensor placement. So even at the top level, I don't want to throw 10 sensors there where 2 would have done the job. So how do I know how many sensors I actually need to place? So this is not our data set. This is the Berkeley Lab data set. So there's a lot of work that Lawrence Berkeley National Lab does on sensors and use of sensors in building energy management. In fact, I'm headed there this summer, hopefully for 3 months to work on this. So this is the Berkeley data set. They had roughly, I think, 50 odd sensors across a setup, one floor of their one of their buildings. And what we were able to deduce from that is how many of these sensors would be really needed to give you an entire temperature distribution across the space that is being covered by the sensors. So roughly a good rule of thumb is 20% of this. So 50 sensors, if they thought 50 is what would be needed, we can bring it down roughly to 10 sensors or so. 10 sensors are enough for us to give a good idea of what the temperature distribution would be across that particular setup. But we haven't actually formalized it yet in terms of how many sensors per square foot. That would be ideal. That is what the government would want from me at the end of the project. Give me a rule of thumb, like how many sensors per square foot. So we have not yet, rough rule of thumb is 1 sensor per 100 square feet or 80 square feet.
Wouldn't that depend on the...
It would depend on the use case actually, yeah. So we are going to, so as far as academic buildings are concerned, we have seen this. Our first real test is going to be when we go to a mall. We are also deploying this in a mall where there's more footfall, where there's potentially more noise. So there we may come across a different rule set. So only after doing the experimentation there is where I will be able to. So you're right, it is very use case dependent. In academic buildings, I think that's a good rule of thumb. In a mall or say in an office, there could be another rule of thumb as well. Yeah? So just closing the loop on the sensor placement problem I was talking about, it's clear that there are models that we need to basically map what is being recorded into what the ground realities are going to be, and we also need to have redundancy in sensor placements, in sensors, because you've seen that some of these sensor data can be faulty, so we want to have redundancy as well. But we don't want to, because we're academicians, we're not running a business here, so we want to be able to come up with a more accurate model, how much redundancy. So the next step for me would be to try and understand sensors themselves so that I can fit a failure model. When is the sensor likely to spew a nonsensical data at me? Once I have an understanding of that, I would want to map that into, okay, if I need this much accuracy for my particular application, how many redundant sensors should I actually have at hand, and so on and so forth. These sort of questions could be more addressed from a very scientific perspective rather than just give rule of thumbs, right? Of course, but then we would also distill it into rule of thumbs because that's what industry wants and that's what even sometimes government agencies want. But before we distill them to rule of thumbs, we would want to look at it from an academic perspective. The other things we are trying to do is we are going to showcase you how occupancy based control could be enabled for using your fans, lights, air conditioners. We are also working on something with Murata Engineering where we are actually trying to do control based on comfort perceived by occupants. So you want to maximize the comfort they feel. Of course, you don't want to do that at the cost of just spending as much energy as you want, expending energy. So minimize energy consumption, but maximize the comfort that people feel. So that's another interesting problem we are looking at. And the next, sorry?
How the control thing?
Sorry?
Not explaining the control thing.
The analytics part, I'll be going over it in a little while, yeah.
Asking about the control action.
Control action. What control action?
For the air conditioners? Yeah, so there are multiple. So we haven't actually, we don't have a set of rules again for the air conditioners, but there are 2 or 3 rules that we know from experience work. One big game changer for air conditioners is the set point temperature. So if you were to, if there is an ambient condition of say 28 degrees outside and you put your temperature, inside temperature to be 22 degrees Celsius. If you change that to be 23 degrees Celsius, there are typically huge energy savings that come about because the cycling.
What's the control there? 23 or 24?
So that's the part, the reason I'm talking about that strategy is because it's not easy. We are still building this, the exercise that is currently being done here is in fact creating a thermal model of the room which will then be used with a working AC model we actually have, and then we'll be able to more solidly tell you what the strategy should be, because sitting in the analytics engine would be this machine which can tell you if you were to change the temperature set point now to 23.
Technologies we are using are controlling
What do you mean technologies?
the
No, the thing we are using is we are using physics cum data driven models. So we have thermodynamic models to map the room. We have models of the air conditioners that come from knowing what sort of control logic is employed and so on and so forth. So it's basically a coupled thermodynamic model, AC being one part of it, occupants being another, and then the third part is the actual building thermodynamic model itself. And the parameters of this come from data.
So the 20 minutes slide, you already got some sensors in the one room.
Yeah.
Okay. In that, you shown some. Can you go to the 23rd slide? Yes, yes.
This is
In
just a
this,
diagram. Yeah.
Energy modeling and after that control
Correct.
strategies. Okay.
Correct.
I mean, up to what part you're already completed?
So we are currently, all of this part is done. We are currently working on these two. So we have a thermodynamic model now.
What is your plan for doing that? Is there any?
So the plan would be, we're first working on a model. The strategies are in some sense only 2 or 3. Okay, we don't want to do anything outside of what an air conditioning remote does. So we would never go inside the air conditioner and change its operating cycle. So we never touch the AC because that violates manufacturing warranty. So everything that you can do with an AC remote, those are the only control vectors available. So you can change the temperature set points.
I understood.
Yeah.
What I am not understood is energy modeling is there and you are controlling the remote. How you are controlling it? What is that control strategy?
So what we are doing, broadly speaking, what we would be doing, I'll tell you where we are now and I'll tell you what we plan to do next, and hopefully you will find your answer in that because I don't have an exact answer for your question. What we are doing now is we are building a model, basically a simulation model, a very detailed thermodynamic simulation model for how all these 7 air conditioners, let's say, affect the temperature in this room. And the model would then implement strategies. So if I was to change the temperature set point of only 2 air conditioners, what would be the... Wait, just don't jump the gun. I'll give you a complete answer and then if you're not satisfied, you ask me questions again. I'll answer all the questions. So once we, so for one strategy would be, for example, you change temperature set points of all the air conditioners of a select air conditioner. The model will tell you what would be the perceived energy savings from that strategy. Then there will be another strategy you could employ. For example, you may run the AC in a different mode. So in a remote, for example, you would have dry mode, cool mode. So if you were to change the modes of certain air conditioners, then you can have another energy saving. So basically by running these experiments, you would have a rough idea of what each strategy would fetch you in terms of either energy consumption or energy saving. Okay. On top of that now, you would have live sensor data coming in. So these are strategies based on some sensor information. If that sensor information changes, for example, you may need another set of strategies. So what we are hoping to do is we are hoping to interpolate basically as conditions change in the room, do these strategies hold or not. So a strategy may be valid in a half filled room, it may be valid to just change the temperature set points, but is that strategy also valid when the room is full or not? We are running those experiments. Once we have that, we'll have a library of options available which would then be used to do exactly what you are asking me to do. But we are still in the phase of populating that library, so we don't have an information for you. We haven't closed the loop on control. We have the bits and pieces ready for it. So we have sensors continuously collecting information. We have models being developed continuously based on whatever information we perceive. We have models being developed also based on whatever actions we have taken. So we are trying to close the loop on, you know, everything that you do is if you think of it from a control perspective, you have a control input you have a state of the system, and the outputs that you are measuring, which is what the sensors are sensing, are a function of both your state and the input. So we are trying to get to that sort of a state space relationship right now, but we are not yet there, which is why we don't know how to optimize on U. Unless you know what your X is, and you know what your u is, and you know what your y is, and you know what the y equal to f of xu is, you cannot solve that problem. So we haven't yet solved the problem. We are in the process of mapping it. But in some sense, we know what the u is, because as I said, we have restricted ourselves to class of actions that a remote can do. So in that sense, we have simplified the problem, but we don't know all the possible temperature variations we could see, all the possible combinations of sensors, the sensor data we perceive, to what could be the actual state of the room in terms of how many occupants, what is the outdoor temperature, and so on. So once we have more data recorded, we will have a more complete model. So we have a half-baked model actually at best.
We tried the thermal model once. The problem with that tends to be that the number of unknowns is very high with the thermal model. So we had done a thermal model of the air conditioner. At that time we didn't have stuff like this, so we did a normal window air conditioner. Then we had tried to put
this
in
is
the
also
model.
normal air, yeah.
So then we did window AC. The second factor was the external impact. You know, what is the temperature outside, what is the humidity level outside. Very drastic change in that.
Yeah.
We had tried to do a model for the room also inside the building, since it was inside. There was, but at that time, and I'm talking about 2009 or 10, but we could not really arrive at a confluence of the one, the model of the AC, the second, the model of the external,
Correct.
and the third was a model of the way things would happen within the room in terms of airflows.
Right.
Because not only would you have the air conditioners going on, you would also have the fans working.
Correct.
Which have a significant effect on the way the air would circulate.
Correct.
Plus the number of people, which was varying. So at that time, I mean, I'm sure you would probably do a much better job.
I'm hoping you would now appreciate the challenge in sort of the model development that we have to face.
We had a big time. And that time what we had done was, since we had simple Windows ACs, and so we had taken these remotes, you know, we opened up the remotes, we put in simple modules, you know, wireless modules. Right. And we had done a similar exercise for a hall about half of this size. It was a lab. And with about six sensor nodes. Okay. And we did the control action also, like the way you were talking about, but it was a simple on-off control in terms of changing the set point.
Okay.
The set point. So,
so that would just dictate when the compressor goes on or off.
Yeah. So that is how the energy saving would be obtained.
Correct.
The problem was that the positioning of the ACs becomes a bigger problem in terms of modeling, because I mean, you would never have a situation where the air conditioner would always be located at the same place in a single room, in every installation. It would change dramatically.
Correct.
And the height would change dramatically, the location would change dramatically. It would also vary upon how close are they to each other. In our case, we had two of them very close to each other. And then there was one at a distance and one at a distance. And that is why getting the model across was extremely hard. So the model approach really did not work well at that time, because of these unknowns, which are, you know, totally out of, you just can't do anything about it.
Correct.
And so what we did was a reversing. Instead of doing analytics with the model, we said, okay, let's take a look at the readings and just do an open dynamic control. Just let the readings flow
like
in.
Like a feed forward in some sense.
Absolutely, a feed forward kind of system. And we were actually able to demonstrate that a significant amount of saving could actually be obtained on the on the power at the end of the day, with the power. And we measured it more in terms of the on and off time of the compressor.
Right.
Yeah, for how much time would it turn on? And
so just the duty cycle.
Just the duty cycle, because that itself gives you what the value is. Correct. And we were actually able to show significant saving. I mean, almost, if I remember correctly, 25 to 30% reduction in the on-off time. Vis-a-vis a situation where you would simply leave them on. And the normal tendency tend to be, keep it at 18 degrees. Just keep it at 18 degrees and let the damn thing work. But like you said, with advanced analytics, perhaps you could do much better.
So we also have a parallel group that's doing exactly the kind of approach you're doing, slightly more evolved in terms of how many decision parameters, because we now are sensing more. Just the fact that we have occupancy sensing, for example, you potentially did not have those readings. So now that's another sensor information that you can leverage in some sense. So same sort of just pure sensor driven or rather sensor data driven analytics is another team that's working directly on that, and it would be fun actually at the end of 6 months to compare which one is going to do better. Because I come from a control perspective, so intuitively I tend to gravitate towards models that come from physics and thermodynamics and so on. But you're right, I mean, even in this room you can appreciate, this is just two walls and two, joined walls have ACs. So in terms of thermodynamics, the worst place in the room to be is that particular corner, because there's no AC that's actually directly cooling that space at all, right? And potentially you guys can be feeling that right now when you are sitting there. And and again, if I move to another room, the placement of ACs is going to be different. So model would change dramatically. But some of these people now are throwing terms like, oh, if you start with the basic model, could it learn? When you have AI and deep learning and everything coming in, people think that everything could be just learnt in some sense, right? I mean, you build a basic model and then you just learn on it and become better. We will either show them if it can be done, or we'll show them how hard it is. So don't attempt it. One way or the other, we'll have an answer at the end of 6 months, hopefully.
This controlling the dimming of the lighting at that time.
Yeah.
This was for 2012.
Okay.
So we also did experiment on the dimming of the light at that time. You can't dim this, it's not feasible. So we had used simple bulbs.
Right.
Simple bulbs, and we were a full loop control action. The problem that we observed there was, and we had defined a term called area of influence at that time, and I think it was published. When you have two light sources, so the impact at any given point of time would be a combination of those. It would not be one alone.
Correct.
Same for the
ACs as well, yeah.
So we had arrived at equation for a area of influence depending upon what would be the impact.
Okay.
The problem was that it became such a complex equation, was very difficult to implement at that time.
Correct.
And I guess that's where we stopped. We defined that equation and we stopped at that.
We can. I would love to talk more about this offline with you. If there are any more questions, I would like to stop at this point.